Score distribution for the first exam is up here. If you're curious as to where you stand as compared to your peers. This particular exam, we had an average of 67 and a median score of 69. We had scores ranging anywhere from, 14 up to 97 on this exam. Now obviously, we're somewhere down here. We're probably not too happy with ourselves. But what I will say is that the second exam typically is the most difficult for most students, and the areas with which I expected some of you would have difficulty with, you did, which we talked about would have been the nomenclature, and we pretty much had those that got them all and those that got very few. And so that will be something though that won't be going away. So if you struggle with nomenclature, you can't just punt it off and say, well, I'm just going to forget about it, because from this point forward, if we talk about something like sodium nitrate, it will be expected that you know what sodium nitrate is. And if you don't know what sodium nitrate is, then it's just like you are going to struggle with those concepts later on. So probably of all the things you've done all semester, that nomenclature will come back to bite you in the butt the most. Next would probably be the mole conversions. Even though the mole conversions was something collectively in this exam you probably did the best on as a class, it is one of those things that we will be getting into again. In fact, we're getting back into the mole concept here today. And so if you don't know how to convert grams to moles or moles to grams, as you'll see, today's discussion is going to be very difficult for some of you. So just because we've already tested on it doesn't mean it goes away. Chemistry is a cumulative subject, just like math is a cumulative subject. You can't talk about multiplication and division unless you first talk about addition and subtraction. And so chemistry, again, is a lot the same way. We can't talk about higher concepts until we first get the lower concepts. And those lower concepts, I understand, is difficult for many of you. Now, the other thing is that if you are, even if you're sitting up here 75, some of you might be saying, well, geez, I've never had a C in my life. I don't really assign grades. Well, I don't assign grades at any point of the semester until the end. And that grade that you get at the end, that's the only time that we really have a letter grade. So you might think of that as a C, but it's not a C until the very end. And if your final percentage is 75%, then yes, that would be a C. Now, what I'm often asked is, well, what can I do to improve? You know, I didn't do very well. And the truth of the matter is that for some people, unfortunately, it takes more practice. Just if I were out, for example, on the basketball court, if I sink one basket, that doesn't mean that I'm going to sink every basket. If I'm going to sink more baskets, what I need to do? I need to practice. And if you're going to succeed on your chemistry, what are you going to have to do? Practice. And some of you may have practiced, you know, like 20 hours, and you still didn't do well. Some of you might only practice like 2 or 3 hours, and you did very well. And that's just the nature of the beast. I can't help that. And that's why we have professional athletes. Those are the ones that probably don't have to practice a whole lot, but they still practice a lot because they want to maintain their skills. And same with the musician. If you're a musician, you can't just go to a concert because you've gone through a piece one time and expect that concert to be the most beautiful concert ever. You have to practice that piece and practice it over and over if you're going to get that piece down very well. So when you come to me and ask, well, what can I do? The basic thing I'm going to tell you is you need to practice. Now, what I can help you on is perhaps what you should focus on practicing the most. But my response is always going to be the same. It's going to be you need to practice. And you just need to practice more, even if you're one of them that already practiced a bunch. There's some that just have more talent than others, and if you want to get up to that level of others, you need to practice more than others do in here, and that's just a fact. And it's not necessarily fair, but that's just the way it is. And in my case, I wanted to be a musician, but no matter how much I practiced, I felt like I wasn't going to be at the skill that I wanted to be at, or where I felt I should be at, and didn't wind up going there, so became a chemist instead. So I wouldn't say that you should write it off. because I have seen students that have been down in this range before still pull off B's and C's in the course. But even then, again, you're going to need to practice if you're going to wind up with that grade you desire. Now, a couple things. Remember that your lowest exam score in here is dropped. Okay, and I wouldn't bank on it already happening, but usually for most students, the second exam, at least as a class average, is the lowest. If it comes to the third exam, that's usually, of the 4 one-hour exams, that's usually about the one that is the second highest. And then the fourth exam is somewhere probably around the, probably about the second lowest. So it just kind of goes back and forth on them. And it's just often reflective of the level of difficulty of the material. And at the very end of the semester, you're going to want to know, well, what am I going to get for a grade? Or how do I predict? And this is where there isn't really flexibility. So if you want to know how you are evaluated at the end of the semester, you go back to the course syllabus, and the course syllabus will tell you how grades are assigned somewhere here. Here we go. And they are assigned on the basis of 90, 80, 70, 60 at the very end. And just because you're a nice person or because you show up every day to class, that doesn't mean that you're going to get the grade that you want. There will be students that will fail this course, and you'll fail the course if you get 60% or below. That's just a fact. And so if you had generous teachers in the past that said, well, if you just show up every day, you're going to pass, that's not the case. These are the standards to which you need to aspire if you intend to achieve a certain grade. Now, the way things that will ultimately work at the end is something like this. Students that score in the 50s on an average on their exams usually wind up with a D because their labs and homework and extra credit tend to bring them up. Students that tend to average in the 60s in their exams tend to wind up with a C simply because the extra credit and homework labs bring those scores up. Students that average in the 70s tend to wind up with a B because, again, those homework and labs and whatever tend to bring up the averages at the end, and of course with the dropping the lowest. And typically those that average 85% or above wind up with an A at the end, again, because those things help. But again, when I say typically, that's assuming that you're doing well on your labs, that you're doing well on your homework, and that you're doing those extra credit practice problems. If you're not doing those things, then pretty much whatever you're averaging on your exams will be what you wind up with here at the end. But in here, a point is a point is a point. And so if you ever want to know where you stand, you can just go to the D2L gradebook, add up your points. And I did not have the percentages displayed until somebody asked me in here yesterday. And so I have those now displayed in there. So at any time, if you want to know where you stand, you should be able to go into D2L and check out your percentages. So with that, any questions that you have? Any questions? All right. Then what we're going to do here today is we are moving on to a new chapter, and we are moving on to chapter 8. All right, that must mean our signal to move on, right? Okay, chapter 8 deals with the concept of stoichiometry. And I always joke around that I probably won't say this word more than about 5 times all semester, because stoichiometry is just the name that's given to it. All right, I'm sorry too. All right, so stoichiometry is the name that we give to the study of the topic, but what we do in it involves the mole concept. And the reaction we're going to look at is nitrogen reacting with hydrogen to yield NH3. And let's see, first of all, if we can balance this chemical equation. So let's start with hydrogen. How many hydrogens here on the left? And on the right? 3. Least common multiple between 2 and 3 would be 6. So how do we make 6 hydrogens here on the left? Put in a 3. And to make 6 on the right, we'd put 2 in here. And then if we look at the nitrogens, how many nitrogens here? 2. And on the right, we'd have 2. And this then would be a balanced chemical equation. So now if we ask ourselves what these coefficients stand for, that is these numbers in front of each of these reactants and products, these are what we refer to as the number of molecules. And we use what's called the molecular interpretation. And I realize that sometimes they are ionic compounds or they are elements, but despite that, chemists still refer to this as being the molecular interpretation of the chemical equation, where each of these coefficients stand for molecules. And what we'd say if we describe it is this. We would say that 1 molecule of nitrogen reacts with 3 molecules of hydrogen to produce 2 molecules of ammonia. And we call it the molecular interpretation, where those coefficients stand for molecules. 1 molecule reacts with 3 molecules to make 2 molecules. Now how about instead, let's say we started with 2 molecules of nitrogen. So in other words, let's say we started with something like this. 2 molecules of nitrogen will react with how many molecules of hydrogen? Okay. And so we could write it something like this. There'd be a total of 6 that are in there. And these would wind up producing how many molecules of ammonia? And again, that would be how many? 4, right? Okay, and so if you counted here, you would see that the number of atoms all add up. We have 4 atoms of nitrogen. We've got 12 atoms of hydrogen. Over here we have 4 atoms of nitrogen. We have 12 atoms of hydrogen. And so we could use what's called a pair interpretation. And in the pair interpretation, the coefficients would stand for pairs. We would say that 1 pair of nitrogen reacts with 3 pairs of hydrogen, making 2 pairs of ammonia. Or basically we multiply each by 2. Or we could use a dozen interpretation. And in a dozen, if we had 1 dozen nitrogen molecules, 1 dozen would react with 3 dozen to make 2 dozen, which would be called the dozen interpretation of this chemical equation. And I always say that's fine if you're a baker, but if you're a chemist, what do you think is going to be most important here? The mole interpretation, right? And in the mole interpretation, each of these coefficients would stand for the number of moles. And so what we'd say then is 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of ammonia. And that would be if we had Avogadro's number, where this would stand for Avogadro's number of molecules. So that would be 1 mole of nitrogen with 3 moles of hydrogen making 2 moles of ammonia, and we call that the mole interpretation. And so with the mole interpretation, we could then do some chemistry with which we are familiar with these terms. We could say something like this. We might want to know if 25.8 moles of H2 react, we'd like to know how many moles of NH3 would be formed. Well, now we're going to set these up a whole lot like we did all of our other calculation problems. We're going to use dimensional analysis. We're going to start with the 25.8 moles of H2. And what are we looking for in this calculation?
Moles of NH3.
Moles of NH3, good. And so then we need a relationship that takes us from moles of H2 over to moles of NH3.
Well, we have the ratio.
And then we use the ratio. We go back to the balanced chemical equation, and I'm going to go ahead and copy and paste this so we can see it down below here. So we'll copy this, and we'll paste it down below here. A little off-centered, but we'll put it back here. So looking at the balanced chemical equation now, we want a relationship that relates moles of H2 to moles of NH3. And what we'd say, and let's just write them down, moles of H2 to moles of NH3, what number would we put here in front of the H2? How many moles are there here?
3.
There's 3 moles here for every
2.
2 moles of NH3. And we call this the molar ratio. This is called the molar ratio. And the molar ratio comes from the coefficients in the balanced chemical equation. Now this symbol here, this is not a mistake, there's 3 lines. Anybody know from your mathematics or geometry what the 3 lines stand for? It stands for is equivalent to. So according to this particular, it's not equal to, because they're not the same thing, but at least according to this equation, 3 moles of hydrogen are equivalent to 2 moles of NH3. Or your textbook, your author will use the ratio with a colon in there and say that there's 3 moles of hydrogen for every 2 moles of NH3. Again, that's called the molar ratio. And what we can do with this then is we can put this into our setup and we can calculate an answer. And so putting it in here, what would we put on the bottom? 3 moles of H2. And on the top would put in
2 moles of NH3.
2 moles of NH3. Again, we're just using this as a conversion factor now. The reason why we put it in this way is so units cancel. And if the units cancel out, we can then calculate this out and take 25.8, multiply it by 2, and divide that by 3. So again, 25.8 times 2 divided by 3. And wind up with an answer of 17.2. How many significant figures should be in the answer?
3.
3. So we'd round this off to 17.2 moles of NH3. And that is the result. Now once you get this, you should ask yourself if this answer makes sense. And the answer to that should be yes, because if we look at this balanced chemical equation, the number of moles of hydrogen, are these more or less than the moles of NH3? Is this more or less than this?
It's more.
It's more. So if you look at this, we have more moles of hydrogen than there are moles of ammonia. This answer does, in fact, make sense at the very end. Okay, any questions on this? All right, let's pull out our electronic devices and get logged into the Socrative app. Got 2 questions waiting for you here. I did not have one waiting for you when you came in today, since we just wrapped up a test. So your first question is going to be related to the same chemical equation. We'd like to know what is the correct molar ratio between N2 and H2. And talk with a neighbor if you need to. There are 31 of you here, so let's get logged in if you're not. It's only showing 26 of you. Remember, I do take attendance this way, so be sure that you get logged in each day. We'll give you about 30 seconds. If you know what's going on and somebody else is sitting next to you still having questions, you can help him or her out. Get up to 25. There we go. 5, 4, 3, 2, 1. Correct choice here is A. There's 1 mole for every 3 moles. Again, where do these numbers come from? The coefficients, exactly. So the fact that there's 1 mole of nitrogen right here comes from the coefficient for N2, which is a 1. And 3 moles of hydrogen because the coefficient here on the H2 is a 3. So we say that the molar ratio is 1 mole of N2 to 3 moles of H2. Any questions on this one? All right, then next, this will require you to determine a molar ratio and then perform a calculation. How many moles of N2 will react with 9.33 moles of H2? We'll count down. 5, 4, 3, 2, 1. And the correct answer here is 3.11 moles of N2, 3.11 moles. So very good, very good. And we get this because the molar ratio, let's start with the top and bottom here. On the top we put in 1, and on the bottom we put in 3. And then dividing this out, we see of course that moles of H2 cancel out. We wind up with 3.11 moles of N2. So any questions on this particular one? All right, now if we go to the lab, we aren't measuring in moles. What are we measuring in?
Grams.
Grams, right. So what we need to remember though is these coefficients don't stand for grams, they stand for moles. And so what that means is if we are working in the lab and we're measuring stuff in grams, we have to take those grams and convert them first to moles. And of course then we're going to use the molar ratio to convert from moles of one to moles of another. And then at the end we're going to have to take those moles and convert them back to grams to figure out where we're at. And that's exactly what chemists do industrially. And we might take a problem something like this. And we're going to use the same problem we've been working with. And that is nitrogen reacts with hydrogen to produce ammonia. And we balance it with a 3 here and a 2. And let's work with this problem here. We'd like to know what mass of NH3 would be produced when 57.4 grams of N2 react with an excess of H2. So I'll give you a chance to write it down. I'd like to know what mass of NH3 would be produced. 57.4 grams of N2 react with an excess of H2. Now I know word problems trip some students up. And for example, you might look at something like this and say, what does an excess of H2 mean? Well, how many of you do grilling at home? Or your parents grill? All right. If you grill at home, you're reacting propane with what stuff in the air? Oxygen. And so if you're grilling something, eventually something will run out. And what is it that's going to run out? Is it going to be the propane or the oxygen in the air?
Propane.
The propane will. So what we could say is if we were talking about grilling something, we could then say that propane is reacting with an excess of oxygen. And so we don't know how much oxygen there is, we just know that there's a whole bunch. We don't need to worry about how much oxygen there is in there, other than there's a whole bunch of it and we don't need to worry about it. And the same is true here when you see the wording with an excess of something else. That just means there's a whole bunch of it and you don't need to worry about the amount of hydrogen because it's not going to have an impact on the amount of product you make. And the other thing we look at here is that this is kind of like the way things work out in the real world. And in the real world, we might say, even if we're working in a factory, we might want to say how much of the product are we able to make, knowing we have so much raw materials. Like in this case, if we knew we had a whole bunch of hydrogen, but are limited by the amount of nitrogen, we'd like to know how much of ammonia could we make out of that process. Or if you're baking cookies, you might want to know how many cookies can I make if this is how many chocolate chips I have, or this is how many flours I have, or how much flour I have. So again, it's kind of similar to the way we do things out in the real world. So to do this one, we start off with what we're given, and we're given 57.4 grams of N2. And what are we looking for in this problem? Mass of NH3. And of course, mass is measured in units of grams. Okay, and of course, whenever you see a big gap between what we're starting with and then you worry. Okay, so yes, there's going to be a few things we're going to fill in between here and here to get to our answer. So when we start with N2, remember our first step here is we need to look at that balanced chemical equation, but we can't use that balanced chemical equation unless we first take our grams and convert it to moles. So that will be the first thing we do. We'll take grams and convert it to moles. Now this was a chapter 6 item. How do we convert grams to moles? Need to go back to the periodic table. Exactly. So go back to the periodic table. And I'm going to insert a periodic table here. Anybody need a new copy of the periodic table? Find one here first. Yep. Anybody else need one? Remember, you can never have too many periodic tables. If you wind up with too many, you can just wallpaper your room at home. Memory. Hopefully a pleasant one. Anybody else need one? All right, so we go to N2. Anybody need a calculator? I have calculators up here. Okay, we want to relate grams to moles. How many grams of N2 do we have? Remember how that works? We're always figuring out the number of grams contained in 1 mole. So how many grams of N2 are there in 1 mole? 28.02. And we get that by looking at the periodic table, and we see that the molar mass, or the atomic mass of N2 is 14.01, not of N2 but of N. And because the formula is N2, we take the 14.01, multiply it by 2, and we get 28.02. So we come back to our setup, and on the bottom we put in 28.02 grams of N2. On the top we put in 1 mole of N2. And that's this conversion right here. We place it into there because we want units to cancel out. Now you realize why we did dimensional analysis at the beginning of this course. So now we have moles of N2. We want to get over 2 grams of NH3. So in order to convert from one substance to another, we need to use what's called a molar ratio. And so the molar ratio that we want in this case is the one that relates moles of which stuff? N2 to moles of NH3. And we picked these two out because these are the two that are in our calculation. So now if we want to relate these two, we need some numbers in here. What number is going to go in front of the N2? 1. And in front of the NH3 would be? 2. And again, those numbers come from the?
Periodic table.
Not the periodic table.
It's a problem.
The problem. They come from the coefficients in the balanced chemical equation. And it tells us that we have 1 mole of N2 for every 2 moles of NH3. So we place it into the calculation. Placing it into the calculation. On the top we put in, let's start at the bottom. 1 mole of N2, and on the top, 2 moles of NH3. Once again, we put it in here so that these units wind up canceling out. Well, now we're just about there. We have moles of NH3. We're trying to get to units of grams of NH3. So how do we convert from moles to grams? Periodic table, exactly. Moles of NH3 to grams of NH3. And what do we call this conversion that relates grams to moles? We call it the molar mass, right? It's a molar mass. So we need to go back to the periodic table, and we see we have 1 nitrogen. And we've got 3 hydrogens, each at 1.008. So we add those up. We have 14.01. Add 2. 3 times 1.008. So NH3 is 1 nitrogen and 3 hydrogens. 14.01 and 3.024. These sum to yield 17.03. So we come back here and we put in. Now where the heck does that 17.03 go? Is it with the moles or the grams? Grams. All right, so it's going to be 17.03 grams for every 1 mole. And we place it in here then, so units cancel. On the bottom we'd put in 1 mole NH3. On the top, 17.03 grams of NH3. At this point, units will cancel out. Once these cancel, our units are grams of NH3. We can then calculate this across. We'll take 57.4, multiply it by 2, multiply it by 17.03, and then divide it by 28.02. And I get 69.773, etc. How many significant figures should be in the calculated result? 3 is what it appears. And if you're confused by the fact that there's only 1 significant figure here, well, this is not 1 significant figure because this is an exact relation, and exact relations have an infinite number of significant figures. So this answer then winds up being 69.8 grams of NH3. And so this is what we call stoichiometry. In stoichiometry, we're looking at the mass and mole relations in a balanced chemical equation. And I think I used up all 5 times now of saying that word. Now, what's important for us here is that we really only learned 1 new thing. We've been here for over half an hour now. We learned only 1 new thing today, and that 1 new thing is a molar ratio. This thing here is an old thing, which we call the molar mass. This is an old thing, which we call the molar. What is this? It's the number of grams contained in 1 mole, which is called a molar mass. The only new thing we learned today is this one, which is called a molar ratio. And again, the molar ratio comes from the coefficients in the balanced chemical equation. So this is old stuff. And remember that when you calculate molar masses are always the number of grams contained in 1 mole. So with this in mind, let's look at another. Oh, first of all, any questions on this one? Okay, let's look at another one. Let's take vanadium reacting with oxygen to produce vanadium 5 oxide. And before we work with any problems on this, what do we need to first do to this equation? Balance it. So to balance it, we leave the simplest one to last, which means we'll leave V to last. We'll balance oxygens. On the left we have 2, on the right we have 5. Least common multiple between 5 and 2 is 10. So to make 10 oxygens over here, we'd put in 5. To make 10 on the right, we'd put in a 2. Well, now this gives us how many vanadiums on the right? 4. So we need to put 4 in front of the V on the left-hand side, and this is a balanced chemical equation. And so with this one here, we'd like to know what mass of vanadium is needed to produce 0.301 grams of V2O5. So let's start this one out like you did before and ask yourselves at the end, what is it we're calculating? Grams of vanadium, which would be V. I'll give you a few minutes to do this. And this then would be, I believe, yep, it is, your next question on the Socrative app. Answer is 5, 4, 3, 2, 1. All right, and it is choice C here. It's 0.169 grams of V. And if we go back to how we set this up, and I took this question a couple different times here today, and it's important. I know it feels like you're writing a lot when you write all these units out, but you've got to carry all these units through, especially when it comes to the molar ratio. And it helps tell you how those units cancel. And so since these are both moles and moles, it is 4 over 2 and not 2 over 4. And again, we need it so the units of moles of V2O5 cancel out. So this is your setup and solution. Any questions on this one? Okay, then let's go on to the next problem here. Let's say that we're working at an automobile factory. And in our automobile factory, our job, of course, is to make automobiles, exactly. So in our automobile factory, we're going to make some very simple cars. We're going to make them out of frames, bumpers, and wheels. And if our objective is to make one car, how many frames will be required to make one car? One frame, exactly. So we have one frame. How many bumpers are going to be required?
2.
And how many wheels?
4.
Okay, so now let's look at this information And from this information, let's take these quantities. We're going to have 50 frames, and we'll have 80 bumpers. Don't yell this out loud now. And 100 wheels. And if we have these materials, the question would be, and this is the next question on your Socrative app, how many cars can we make?
25.
So again, how many cars can we make? Get your answers locked in here. 3, 2, 1. Correct answer is 25. Correct answer here is 25. Now, how do we get that? Well, now, one of the reasons why I wrote it out like this is I want you to think of these as being the coefficients in the balanced chemical equation. And so this will be a whole lot like doing our molar ratios. And so what we're trying to do is we're trying to convert over here to cars. And if we think of these as molar ratios, and I realize some of you got to the answer a lot faster, but if we want to convert from frames over to cars, we could use what is in effect a molar ratio here. And on the bottom we'd put in 1 frame, on the top we'd put in 1 car. And when these cancel out, we wind up with an answer of 50 cars. Very simple. On the next one, if we want to do this as a molar ratio, on the bottom we'd put in 2 bumpers. On the top we'd put in 1 car. Again, we get these from the coefficients in this balanced equation. And bumpers will cancel out. If we take 80 divided by 2, we wind up with an answer of 40. And then if we look at the last one, we want to convert wheels to cars. So on the bottom we'd put in 4 wheels. On the top we'd put in 1 car. Again, because those come from these coefficients in this balanced equation. And if it's 4 to 1, what will happen is that wheels will cancel out. And we take 100 divided by 4, which is going to give us an answer of 25. And so now we see 3 answers. We see 50, we see 40, we see 25. And the correct answer is 25. And why would the correct answer be 25? Yes?
Because it's the limiting factor.
What's the limiting factor?
Wheels.
Wheels. And what does it mean if we say it's the limiting factor?
It means you can only make as many cars as you have of that specific.
Exactly. We can only make this many cars because once we get up to 100 wheels, what's going to happen?
Any cars you make afterwards won't have wheels.
Yeah, any cars after that won't have wheels. So if we want to make a complete car, we've run out of wheels. So at this point, then we'd say that the correct answer is not going to be 50, it's not going to be 40, it's going to be 25 cars. And we'd say that the 100 wheels in this case are what we call, using your terms here, the limiting factor. We actually call it a limiting reactant. And we define the limiting reactant as being the reactant, this is the reactant that limits the amount of product. That can be made. So again, it is the reactant that limits the amount of product that can be made. And the 25 cars, this is what we refer to as the theoretical yield. In other words, in theory, we should be able to make up to 25 cars. Now, borrowing from our previous wording, we may have said something like this. We may have said, how many cars could we make if we had 100 wheels and an excess of bumpers and frames? So that's where that excess comes into play. We have an excess of bumpers, we have an excess of frames. We don't care as long as there's enough to make them, but we wind up using up all the wheels, which in this case is the limiting reactant. And then if we want to define what that theoretical yield, we say that the theoretical yield is the maximum amount of product we can make. So the maximum amount of product we can make when all of the limiting reactant is turned into product. So again, the theoretical yield is the maximum amount of product that can be made when all of the limiting reactant is converted into product. But now there's a reason why we call it the theoretical yield. We might say if the actual yield was 23 cars, we'd like to know what is the percentage yield. Now, why might we wind up with 23 cars instead of 25? Defects, sure. We could wind up with some defects. So when we talk about the theoretical yield, again, the theoretical yield is the maximum yield when all the limiting reactant is converted into product. But if we're out in industry, the reality is that there could be some defective materials, and the actual yield may turn out to be less than the theoretical yield. So in this particular case, we would say that the 23 cars would be the actual yield. So now, don't shout out this answer. This one is the next one on your Socrative app. We'd like to know what is the percentage yield. And I realize I did not tell you how to do this yet. But if we made 23 cars from 50 frames, 80 bumpers, and 100 wheels, what is the percentage yield of cars? So think about, what does percent mean? Percents are always calculated by taking what? Part over the whole and then multiply by 100. Exactly. So I'd like to know, what is the percentage yield? Percents are always part over the whole times 100. Five, 4, 3, 2, 1, and it's 92% yield. We get the 92% by taking the part, which is 23 cars, and dividing it by the whole, which is 25 cars, taking that result and multiplying by 100. Cars will cancel out, giving us a 92% yield. And so in chemistry terms, what we say is that percentage yields are calculated by taking the actual yield, dividing it by the theoretical yield, and taking that result and multiplying by 100. Okay, we have about 11 minutes left today. Are there any questions on these materials? Okay, here's some problems at the end of the chapter. 23A and B, 33A and B, and 43A and B. And these would be on pages 274, 275, and 276. If you don't have your textbook with you here today, please look off of someone who does.